Quick announcement. No, couple of announcements. So first, I was at GE this week for my conference travel, and it turns out GE is hiring a lot. GE Vernova, which is their energy wing, but so is GE Aerospace, which is their aerospace wing. So we will have a distinguished seminar speaker in the ECE department from GE Aerospace 2 weeks from now. So be on a lookout. If you're not in ECE, how many people are not in ECE here? Okay, a few people are not in ECE. So I'll try to send out the announcement to the entire class about that particular conference, about that distinguished speaker. So that way you will have some chance to interact with him after his talk and see whether your profile can fit within GE Aerospace or not. But if you're looking for an internship or if you're looking for a full-time role, if you do computer vision or machine learning or AI or whatever, uh, including some mechanical stuff, GE Vernova has a few positions open. GE Aerospace also has a few positions open, or if they are not open now, they'll be opening up in the future. So just be on a lookout, and if you're interested, let me know. Two of my students are ex-students are in GE, so they can give you an internal referral, which will help you, help you with your interview process. The second announcement is many students have come to me that they are not available on the week of the midterm. So I'll try to figure out if there is an alternate day that works for everyone. And if so, we'll move the midterm to an alternate day. If not, then we'll figure out what to do with those people who cannot attend midterm. Most likely, I'll have to create another midterm for them. And then I'll have a separate midterm for those 5 or 6 people who have come to me about their non-availability. So I'll again send out an email and with a poll or a link or something, and then we'll figure out if everybody is available on a specific date. I would prefer to have a midterm on that particular date. I don't want to create another midterm, but if that is the need of the hour, then we'll do that. Okay, moving on to our discussions on the accelerated methods. This is in the previous class, I didn't remember the algorithm. I didn't remember the conditions because I wasn't prepared for it. But this class, I'm prepared for it. So let's talk about that. I want to minimize a function. X is in Rn. And our goal is use gradient of fx naught, gradient of fxk to compute dk. So far we were discussing about how to compute dk only with the knowledge of gradient of fxk. And we were talking about, let's take the second derivative, let's invert some matrices, let's approximate some matrices, and then try and solve the problem. But this time, I want to make sure that my dk, the descent direction, depends on a whole bunch of gradients that I've computed so far. And this particular problem was studied back in 1970s. So remember that BFG and DFPS method, all of these methods also comes from 1970s. So 1970s, a lot of people were working on problems of this type as to how do we use the sequence of gradients that we are computing in order to speed up the optimization algorithm. So I'm going to make an assumption for today's class. My assumption is that the second derivative of the function has the smallest eigenvalue is m and the largest eigenvalue is capital M for all x in Rn. So to give you to come up with an example, so if f of x is half x transpose qx, or maybe just half is fine, half x transpose qx, then m equals to lambda min of q and capital M is equal to lambda max of q, and both of these are greater than 0. Remember, whenever we are taking a quadratic function, we want to make sure that our q is a positive definite matrix.
Is there a name for those type of functions?
There is a name, but I don't want to confuse people here. So I think the name for function that satisfies this is smooth, and the name for function that satisfies this condition would be strongly convex, right? So this condition means that the second derivative of function is always positive definite, so it must be convex. So you say strongly convex and smooth satisfies this class of conditions. Actually, it's a good point. Let me just write it. The name is, because if you're reading research paper, this is what they will say: strongly convex and smooth. If you're reading a paper, you will read this term strongly. Let f be a strongly convex and smooth function. This is exactly what they mean. If you're in practice, if you're working on an optimization problem, it's quite likely that this particular assumption would be satisfied. So I wouldn't worry too much about this assumption, but certainly you can always construct pathological functions, or you might have certain problem structure where this condition may not be satisfied. But to a large extent, this problem will always be satisfied for reasonable problems. But definitely one case where it's not satisfied is neural network training, because that's not a strongly convex function. Yeah. Okay. Any other question? So if you go back to the 2024 lectures, I mentioned about the derivation of Nesterov's accelerated gradient and Poliak's momentum method. But today I'm not going to do the derivation of these methods. I'll straight away jump to the algorithm, and I'll tell you why this algorithm is faster than the typical steepest descent algorithm. Nesterov accelerated gradient zk equals to yk beta k So that's algorithm number 1. I have algorithm number 2, which is Poliak momentum method. Alpha k. So these algorithms are good because we don't have to compute any matrix inverse. I just have to pick two scalars, alpha k, beta k greater than 0. That's it. Everything is linear in this expression. These algorithms are discussed in Intro to Convex Optimization. Page 70 plus. And it gives you the derivation of these algorithms, where these algorithms came from, what are the essential underlying mathematical structure that is exploited to come up with these algorithms. So don't think of it as there are only these two accelerated gradient algorithms and there is nothing else. You can go back to the book, you can look at the recipe, and you can create your own algorithm. But these are the two that are very well studied in the literature. These are the two algorithms for which hundreds of papers have appeared in the past, and people have tried these algorithms on a variety of problems. So that's why we study these two algorithms. But there is a recipe, and feel free to read the book and come up with your own algorithm for fun. If you don't have anything better to do on a Friday evening, you can create your own algorithm. Okay, so what I want to do is I want to tell you why this algorithm is better than the steepest descent. And in order to do that, I'm going to pick this function, the usual quadratic function, because we know what the optimal solution is. X star is equal to 0. Q is positive definite. So M equals to lambda min of Q. Capital M equals to lambda max of Q. The steepest descent method is xk plus 1 equals to xk minus alpha qxk, which is given by I minus alpha q xk. How do we measure the speed of convergence? How do I know how fast this algorithm is going to converge? So if you go back to our first, not maybe first lecture, but second or third lecture, remember we mentioned that the spectral radius of this matrix determines the speed of convergence of this algorithm. So I look at the spectral radius of I minus alpha q, and that will tell me how quickly this method is going to converge. And you pick alpha equals to 2 over capital M plus small m, then you get the fastest convergence. Okay, so that's steepest descent. Let's look at Nesterov accelerated gradient method. How do we study the structure of NAG, Nesterov accelerated gradient method? What would you do if I ask you, let's say today is midterm day, and I ask you, study the convergence of this algorithm? What will you do? What's step one?
Maybe we can express it in kind of a linear form.
Yes, so we want to put this in the linear format. How will you do that? Yeah, perfect. So I'm going to write it as a larger state space problem. So this is, by the way, this is a very important proof technique. So don't think of it as just some random stuff being written on the board. This is exactly how you study the convergence of accelerated or convergence of algorithms. So remember, this algorithm involves two separate variables. One is yk plus 1, one is zk. So I have to come up with a what is known as a state space for this algorithm. Okay, so I'm going to pick zk plus 1. So one thing that you will notice is I want to write these two variables in a way that the same set of variables with a one time step below appears on this particular side. Okay, so I have to pick zk plus 1. So if you look at it, it contains yk and yk minus 1. So that becomes a problem. So if I pick zk plus 1, then I have yk plus 1, and then I have yk here. So then everything will become a function. Oh, this is not xk, sorry, zk. Yeah, it's zk, sorry. Can you make that change? This is zk. Okay, so On this side, I'll only have zk, and on this side, I'll have yk plus 1, and I'll have yk. So something that is purely a function of zk and yk. So zk plus 1 can be given by, I might have to erase this side because it's a fairly big matrix. 1 plus beta I minus alpha q minus beta I So in this case, I'm going to pick alpha equals to 1 over m and beta equals to square root. Okay, so I was given an algorithm. I massaged the algorithm in a way that I get a set of variables here and then the same set of variables with a one time step lower on the other side, and I came up with a matrix in the middle. Now, of course, alpha and beta are free parameters. We can pick howsoever way we want. Both of these parameters are strictly positive. So I pick the parameter according to these requirements, and then what I can show is that the spectral radius of this matrix is less than rho of I minus alpha q, where alpha value is given by this expression. So this is the best alpha for steepest descent. This is the best alpha beta pair for the Nesterov accelerated gradient. And with the best alpha beta, you get a spectral radius which is strictly less than the spectral radius for the steepest descent. What that implies is Nesterov accelerated gradient method is strictly better in terms of convergence. It's strictly better than steepest descent algorithm. It's not as fast as Newton's method, but it's certainly better than steepest descent. Why would you not want to use this algorithm? What's the problem with this algorithm? This is a better algorithm than steepest descent. So if you're using steepest descent, it's better to use this algorithm. Why would someone tell you that this algorithm is bad?
We have n variables, but we need to deal with the two n variables.
Yes. So you started with n dimensional vector, but now you are dealing with 2n dimensional vectors, right? So if your n is very large, what was the size of GPT-5 or GPT-4o? 1.8 trillion parameters. So n is 1.8 trillion there, but in this particular algorithm, you need to have 3.6 trillion parameters. So you don't want it. Okay. Same thing, if you have a very small device, a very small microprocessor, and you need to run this algorithm, some optimization algorithm, this requires only n variables in the memory. This requires 2n variables in the memory. You know, I'm telling you about these optimization stuff. So let's say you go to GE Aerospace or you go to GE Vernova. They care about the fact that you're using a microprocessor that is 50 cents versus 25 cents. It's really important for them to reduce those costs. Now, with a 25-cent microcontroller or microprocessor, you may not be able to run this kind of algorithm, but you can run this kind of algorithm. And one of the things you should know is, if you go to any of these companies, one of the strong focus now is energy efficiency. Okay, you want to get more thrust out of the same engine, you want to get more energy out of the same wind turbine or a gas turbine. So they are all spending incredible number of hours trying to optimize their wind turbine, their gas turbine, their engines in order to improve the performance. And whenever somebody is doing optimizing engines, what they are doing is running some algorithm of this type. I mean, of course, it may not be an unconstrained optimization, so they may be running some constrained optimization algorithm, but they are running some algorithm on a microprocessor to execute. The other thing is, of course, in this class, almost all of these algorithms can be, you can pull in a Python package and you can write these algorithms in like 2 sentences. But if you go to GE Vernova or if you go to GE Aerospace, you are actually writing the actual C code and executing it on an actual microprocessor. So that's why these algorithms will be very much needed in those situations, because you can't pull a package and get done with the work. Okay, so next order of accelerated gradient is strictly better. Let's look at Poliak's momentum method. What should my state space be in this case? Poliak's momentum method, what's my state space here? Somebody wants to help? Right. So I have 1 plus I don't have the beta and alpha value, but once again, the spectral radius of this matrix is much lower than the spectral radius of I minus alpha q. Okay.
Can you explain gradient of gradient?
This one?
Yes.
Yeah, so that's why I have I minus alpha q term here. That's the gradient, and then beta I is this term, beta times xk term, right? And then minus beta I is this term, beta times minus xk minus 1. Okay. So why are we getting a better algorithm here? So we have increased the dimension of the system. So I'm using system because I come from a control systems background. So I always think of everything as a system. But what we have done is we have expanded the dimension of the optimization, like the dimension in which the optimization algorithm is running. And because I have multiple free parameters to pick, so here I have only one parameter alpha, I have beta and alpha here, and I have a special structure in the matrix. So by picking an appropriate alpha and beta, I am able to reduce the spectral radius of this matrix in comparison to the spectral radius of this matrix in this higher dimensional space. As a result of which, I am able to get faster convergence. The computational complexity is not much, okay? You just have to increase your memory, but the complexity is not that difficult. I mean, addition, subtraction, all of that is simple and straightforward operation. Okay, any question? Yes, please.
So for the state space representation, why did you include, the second row that doesn't really tell you anything?
Yeah, so the reason for that is your original algorithm involves 2 separate variables. So if you want to study the convergence, you have to look at 2 variables together. You can't just isolate it. You just can't look at this variable in an isolated way and expect to derive the convergence guarantee.
So even like for the PMM case where we're just saying like x of k equals x of k.
Yeah, that's exactly what I've written. So x of k equals to x of k. That's right.
And we're just doing that to compare like
the spectral. So I've got a matrix representation, and I can compare the spectral radius of this matrix and spectral. These are all square matrices. So I can compare the spectral radius of these matrices. Remember, spectral radius is a scalar, right? So even though I cannot compare these matrices, I can compare the spectral radius because it's a scalar. Any other questions?
Alpha and beta terms, do we know them or?
You generally don't know them. So you can do two things. You can do trial and error and you figure out which one is getting you faster convergence. So hopefully, like let's say you are working on an electrical machine, on day 1, you don't know what alpha and beta is going to work. But on day 30, you have figured out that this alpha beta gives you the best performance for this particular electrical machine. You write that code and then you put it in production. And then that alpha beta is getting used for that electrical machine for the next 30 years that this machine is going to be in the field. Okay?
Here we know that S alpha and beta.
Yeah, that's because I know this Q function and I know what this lambda min and lambda max looks like. So alternate option is if you know the objective function, you do the second derivative and you figure it out. The problem with that approach in general is, let's say you have a big gas generator that you're trying to optimize or a big wind turbine that you're trying to optimize. It's going to be in the field for the next 30 years. So whatever objective function, it might include some gear ratio, some what the friction coefficient between some two things are and all that stuff. After 30 years, things will degrade, some components will get replaced, things will change. So this Q matrix is actually going to change over time. So whatever small m and capital M you have picked on day 0 when the machine is absolutely new, everything is working beautifully, is not going to be the case 30 years down the line. So you want to make sure that you are a bit robust and not picking some best alpha and beta for today, and then 15 years later it just blows up the machine because it's not the best alpha and beta for that particular point of time. Okay.
How they compare against one another, nature of acceleration and volume? Do you know them?
I don't really know that on top of my head. I'm sure somebody would have done some study in some paper or book. I just haven't read it. But you can pick appropriate alpha and beta and you can plot the spectral radius and you will see under what condition which algorithm is better. I just haven't done that exercise myself, so I don't know. Yes?
Can we write energy fully in terms of y?
No, you cannot, because zk is always an intermediate variable. So if you want to write it in terms of y, then you will have to expand on the zk.
Yeah.
And then you will have yk and yk minus 1 as the state variable.
Yeah.
So instead of having zk and yk, you will have yk minus 1 and yk as the state. Then it will become very similar to this. That's right.
So these two methods are all like 2 steps behind.
That's right. Yeah. Okay. And if remember, I mentioned that the derivation is given in this book. So you pick a different sequence, like let's say you construct a different estimate sequence functions there. You might have 3-dimensional terms here, and it might be better. Okay, by picking appropriate alpha, beta, gamma, you might get a better algorithm in that case. And you can give it your name, my algorithm or whatever.
For the convergence, we were able to kind of express in linear form, but for Newton algorithm, for example,
yes,
contains some inverse.
That's right. That's right. Yeah. So this is a linear form because my function is quadratic. If my function is a general function which is just strongly convex and smooth, you can't actually do it in the matrix format. Then you have to do it using a technique called Banach contraction mapping theorem that we will cover maybe a month from now. Okay, end of October. That's when we'll cover that result. So that's why I'm picking an easy function, because I can show everything in terms of linear algebra. Okay, and as the class progresses, things will become more difficult. Your brains will get more trained. Then I'll throw the hammer in front of you, and then you will see how it works in general spaces. Okay. No other question? Okay, so let's. I'm going to keep this stuff here, but I'm going to change the algorithm and I'm going to change the goal a little bit. So one problem that you tend to get, especially if you're solving very high dimensional problem like training of neural networks, is you don't quite know how to pick the step size. So you still want to use gradient methods, but you don't want to, you don't know how to pick a right step size. So let's talk about those class of problems. So I have two algorithms like that. One is AdaGrad. I think this is 2009-ish. I shouldn't write 9, but 9-ish. So it came out around that time. The algorithm is xk plus 1 equals to xk minus alpha dk. dk equals to gradient fxk over bk, and bk equals to square root bk minus 1 square and you pick b minus 1 equals to is greater than 0.
Sure, the BK minus 1 is greater than 0.
So b0, so when you are k equals to 0, then you have to pick b0, right? So I'm just picking some random b0.
Is it gradient or decision?
This is the gradient. So I'm taking the gradient, I'm taking the norm, and I'm squaring the norm. And I'm adding it to the previous bk square. So that is AdaGrad, and then there is Ada delta. Two 2011-ish. I could be wrong by a few years here, but same algorithm, but beta k square, bk square is beta times beta k minus 1 square. Okay, so what is the salient feature of this algorithm? So remember, my step size here is alpha over bk, right? So that's the step size I'm picking. But bk itself accumulates all the gradient information that has been computed so far. The same thing happens here, but now with a discount factor. So beta is a discount, beta is between 0 and 1. So you pick something between 0 and 1. So now bk minus 1 is multiplied by something between 0 and 1. And then the rest of it, you add up the second derivative square. Why is this algorithm important? So what generally happens is you don't quite know how quickly your gradient of f is going to converge to 0. So as gradient of f is converging to 0, this term converges to a constant. Remember, if this term is 0, then bk equals to bk minus 1. So now your step size has stabilized and you're using that constant step size to get to the next iteration, right? So if this one is close to 0. The same thing happens here, but then you want to make sure that this term is strictly greater than 0, so you add a small positive constant so that this bk square is always strictly positive. Okay, so this is this ADA stands for adaptive. So if you're using PyTorch or any of these TensorFlow kind of packages for doing optimization, you will see ADA grad and ADA delta kind of methods for gradient descent. And ADA stands for adaptive gradient method, then adaptive, I don't know where delta came from, but adaptive delta. No, I know why there is a delta. Maybe it's beta bk minus 1 square minus gradient fxk square. So I guess this is where the delta comes from. Delta stands for some subtraction. So this is where probably the subtraction came from. I don't know, but it's called ADA delta, and both of these algorithms are used for training neural networks, especially for smaller neural networks. You don't use it for very large neural networks, and they have good convergence property. Okay, so this is an adaptive method where what you are adapting is not the way the gradient is computed, but how the step size are selected over time.
Alpha term is it 0 and 1 or something, or
Sorry?
alpha term, yeah, alpha. Is it constant or?
It is constant. Any other question? Okay. Wonderful. So I think if I have to recap, so we are done with the unconstrained optimization. So what happens in unconstrained optimization? I have a function f of x where x is unconstrained. X can go all the way to infinity. So this is an unconstrained problem. We came up with steepest descent and Newton's method class of algorithms, which hopefully converges to an optimal solution by an appropriate choice of step sizes. But then we said, look, we are computing all these gradients. Why are we throwing them away? Let's try to use this. So one idea was, I'll use the gradient to compute the second derivative inverse. Okay, so that idea came from 1970s. Then, so that was quasi-Newton method that we talked about in the previous class. Then we said, okay, I don't want to compute matrix inverse. The whole thing looks very complicated. So let's try to figure out if I can just use a linear combination of the matrices that I've computed so far, because linear combination sounds much easier than matrix inverse. People said, okay, fine, let's do linear combination. Then people studied, Nesterov and Polyak studied those kind of algorithms, and it's covered in this particular book. And we came up with accelerated gradient methods, including Nesterov's accelerated gradient and Polyak's momentum method. Okay, then people said, so that was again late 1970s, early 1980s. So those were the algorithms. Then more recently, people said, look, I'm doing this big neural network training. I don't want to even go through this Nesterov's stuff because it requires me to have more memory in my system. So all I want to do is pick the right step size. So then what is the right step size? Where you include all the information that you have computed so far. So then somebody said, look, the right step size would be, I pick a constant step size here and then I divide the gradient by some factor, and that factor somehow takes into account all the previous gradient information. And then somebody said, look, this one doesn't seem to work well in reality, so let's pick ADA delta, which seems to work well in reality. And then they wrote papers and proofs theorems and whatnot, and we're not going to do that in the class. Okay, but hopefully this lays out the land for, if you were to solve an unconstrained optimization problem at whatever company you go to in the future or whatever research problem you're doing, you have a whole bunch of algorithms to pick from, and you can make the most appropriate choice through trial and error, like what algorithm is best for your device, for your computational complexity, Sometimes there are also what is known as functional safety requirements. So you want to be able to execute the entire optimization within 50 milliseconds on the specific hardware. And if you cannot do it in 50 milliseconds, your algorithm will be rejected by the security people or by whoever is the ultimate authority there. So, so that's why you have a whole bunch of algorithms, and you can pick the right algorithm that meets the functional safety requirements, that meets all the functional requirements that are required by the algorithm. And if those don't work, you end up not doing any optimization. You just have a rule based. If the temperature is above 72, you start running the air conditioner. If the temperature is below 71, you stop the air conditioner, right? So that's a rule based method. So if you don't want to optimize, you implement a rule based method which gets executed in microseconds. So then you meet the functional safety requirement, which is 50 milliseconds. Okay, let's move on to the next topic, which is optimization over convex sets. Okay, so now, until now, there were no constraints. Now I'm going to add a constraint that now the optimization has to be performed over a convex set. So let's look at that. So my problem here is that I want to minimize f of x. X is in capital X and capital X in Rn closed convex set. Why do we need closed convex set? I mean, why do we need closeness of the set? Why can't we have an open convex set? What's the problem with open convex set?
The solution will not exist if it is open.
Solution may not exist if it is open, but does closeness doesn't imply that a solution would exist. But there is something related to that. So remember, we are talking about algorithms, and the algorithms have to converge. So your xk is converging. You don't want it to converge to a boundary because boundary is not included in the open set. Okay, so that's why we need closed convex set. So that if we are constructing a sequence and the sequence converges, it has to lie within the convex set. It shouldn't go outside of the convex set. So what are the examples of closed convex sets? What are typical sets over which we do this optimization? So x is equal to x such that a is less than equal to x is less than equal to b. A and b are vectors in Rn. So this is element-wise inequality. I think we touched upon this inequality a few months back, but not a few months, but a few weeks back. Let me show you. So my 1, 2, 3 is less than equal to 2, 5, 8, but 1, 2, 3 is not less than equal to 2, 0, 5. Okay, so this is element wise. So you look at the first element here, if it is less than equal to, great. Look at the second element, less than equal to, third element, less than equal to. So the vectors satisfy this criteria. So this kind of sets, it looks like a box, like an Amazon package. So this would be your vector A, this would be your vector B, and every point in the middle, any point here within this box is between A and B. So A is one of the corners, B is the diagonally opposite corner, and every point within that set is satisfying this particular condition. Okay, so this is a box set. Okay, that's first example. Second example, x is equal to x such that x is greater than equal to 0. This is known as a positive orthant. This is known as a subspace. Yes.
For number 2, why is it closed?
Because you have an inequality like x is greater than equal to 0. So that equality, that boundary is included.
But towards the...
But only towards the positive side. So let me show you. It's this area, including this line. Including this line.
What if the coverage is to infinity?
That's fine. It's part of closed convex set.
Oh.
Yeah. So if your algorithm is converging to infinity, it means that you don't have a well-defined optimization. Either your algorithm is wrong or your optimization problem itself is wrong. Okay. What about subspace? So subspace looks something like this. It would look like a hyperplane that's passing through origin. That's a subspace. Fourth is x equals to x such that ax equals to b. This is a hyperplane. Five is x equals to norm of x less than equal to r. This is known as a ball in LP norm. And then sixth, less than r. Less than r. So this is ball in LP norm, and the sixth one is x1 xn convex, then x1 intersection x2 intersection xn is convex. I mean, this is closed convex. Closed.
Do they need to be finite?
No, it can be infinite also, but we'll never encounter those situations in this class. Okay, so an example of such a set X is X such that Ax equals to b, x greater than equal to 0. So it's an intersection of set 2 and set 4. Let's look at each of these. So I've drawn subspaces, then Ax equals to b. That's a hyperplane. This is Ax equals to b. This is Ax equals to 0. This is x greater than equal to 0. This is my norm of xp less than equal to r. This is a unit ball. It looks like a diamond, but it's actually a ball. Okay. When will it actually look like a ball? When p is equal to 2. So only in L2 norm, the x less than equal to r looks like a ball of radius r. But if p is something other than 2, then it might look like a diamond or it might look like a square. And this kind of set looks something like this. It looks like a polygon. This is your sixth. Ax equals to b, x greater than equal to 0. So that would look something like a polygon. Or if it is not a polygon, it might look something like this. Oh. So if it is not like this, and it goes all the way to infinity. Okay, so these are the different convex sets that people are interested in. Depending on the application, you might encounter one of these convex sets. And the goal here is I want to minimize the function over these convex sets. The reason why these class of problems are important is, of course, because these sort of constraints appear quite a lot in real world problems. If you are solving inventory optimization problem, or if you're solving some sort of like in electricity, in electric grid, if you're trying to solve some problem, or if there are some constraints, linear constraints, and these kind of problems appear. Sometimes you want to pick these algorithms because what you do is, suppose you have a non-convex set, suppose this set is x is non-convex, you try to come up with the biggest convex set within that non-convex set, and you tend to apply these algorithms. So that's why there are various reasons why we study these kind of algorithms, because optimization over convex sets, there are lots of good, cool algorithms that we are going to talk about. So this one is easy to solve. If I have a non-convex set, that problem is more difficult to solve. So whenever you encounter a difficult problem in optimization, what you want to do is convert it into a problem that you already know how to solve, and keep changing that problem time after at every point of time. So you have an outer infinite loop, and then you have an inner infinite loop. Okay, the inner infinite loop is easy to solve problem. Outer infinite loop is more difficult to solve problem, and eventually you converge to the optimal solution. So we'll talk about necessary and sufficient conditions for optimality in the next class, and then we'll jump right into all kinds of optimization algorithms. I have my office hours right after this class, so if you're interested in talking to me about anything, feel free to talk to me right after this class. Thank you.